Hello students, welcome to Sri Jendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 3 of unit views. So let's begin with today's class. In today's class we are going to discuss first with the speed of traveling wave. Let's begin. So to determine the speed of propagation of a traveling wave, we can fix our attention on any particular point on the wave. Let's suppose the situation is something like this, that this is the wave and it is traveling something like this. Then if you observe, let's suppose this point P, that at a certain instant of time this point it is at here, and at certain other instant of time this point will be at here. If you observe this distance between these 2 points, as you can understood that this is the lambda. Yes, so speed of the wave can be given as, let's suppose the relation is y of xt is equals to a sine kx minus omega t. While I have written kx minus omega t, that means it is moving in positive x direction. And let's suppose if I understood at this location and this location, the new location could be written it's a k into bracket x plus delta x minus of omega into bracket t plus delta t. So this could be it's a k into delta x minus of omega into delta t would be equals to 0, because we understand that kx minus omega t remains the constant. So if I took a ratio of this, it's a delta x by delta t, that would be equals to omega by k, and this could be given as a v. So this v, it's a velocity of a wave that has been given as v is equals to omega by k, or this could be represented as omega is equals to 2 pi by t, or lambda could be given as it's a 2 pi by k, and from this it could be having a lambda by t, and 1 by t it's in frequency, so n is the frequency, and lambda it's a wavelength that we understood. I hope this is clear. So this is the velocity of a wave, or we should say it's a speed or velocity of a traveling wave. We have even derived this when we used to discuss the in first lecture about the simple harmonic progressive wave. Yes, one more time here. So I hope this is clear. Is it clear? Is it great? Now what we are supposed to do is, now we are going to discuss about the speed of a transverse wave on stretch string. Let's see how we will do this. So basically what happens now, whatever we are going to study, basically we are going to discuss about the two waves. One is the wave that has been produced in stretch string. This is something like this, that this is the rigid support, and with this rigid support a one string has been attached, and if you are going pulse from here, then a certain wave has been developed. So we are going to study this as a first case, and second it would be the sound wave. So we are basically having two tasks. This is first task, this is second task, and we are going to cover them one by one. I hope you understand. So now onwards, whatever we are going to discuss is all about either of this wave or this wave. Yes, up till now whatever we have studied, it was all about the generalization of a wave, that how wave propagates, what should be the simple harmonic progressive waves, or what is the traveling wave, how wave travels, and each and everything. But whatever now we are going to discuss is all about the general, is specific one, and that is belong to either of this. It's a wave that has been produced in stretch string, or it could be a sound wave. So let's begin our discussion with the speed of a transverse wave on a stretched string. So let's suppose this is the certain segment of a string, and it has been stretched by here, and when it has been stretched, it is having the tension force T. So when they are having a tension force T, I can make in this angle as a theta, and this would be as in theta. If I took a smaller segment, it's a dl. So if this is T, this is theta will give me a T cos theta. This is T, this theta will give me a T cos theta. So this is a downward direction force. This will be equals to T sin theta, and that is what we call as a 2T sin theta. So this T cos theta and this T cos theta are going to cancel out each other, but the resulting force will give me the net force, which is equals to 2 into T sin theta. As we understand that this theta would be very small, so if theta is very small, I could write sin theta approximately equals to theta, and so that this is 2T sin theta, that would be equals to theta. So this is equals to 2 into tension force into theta, or I should write it as a Fr is equals to T into twice of theta. Now we are having the relation which gives me theta is equals to arc divided by radius. So I can replace this theta or 2 theta with the help of dl by r. This is the relation number 1. As well as let's define one more term. Sorry, that is what we call as a mu, which is mass per unit length. So for a smaller segment of length dl, the mass per unit length is denoted as a mu, and that mu would be equals to dm by tl. So let's took the element of string that is moving with velocity v in an arc of circle, and when it is moving in a circle, it must have a centripetal force towards the center of the circle. So this centripetal force would be equals to dm into a, and this dm into a could be given as dm into a could be replaced by v square by r. So we are having basically two relations, and this was the first relation, which is Fr is equals to T into dl by dr, and this is the second relation, which is Fc is equals to dm into v square by r. If I am supposed to equate this two, then this dm into v square by r, that is equals to T into dl by r, and from this it's a mu dl into v square, that is equals to T dl. So if I remove this, it's a dl has been gone, and I have been left with v square is equals to T divided by mu, or it should be v is equals to under root of T divided by mu, where T is the tension force acting on string or at that particular point, and mu, it's a mass per unit length of string. Mu is the mass per unit length of the string. So this is the one of the approach to derive the formula when wave is traveling on a stretched string. We have a different approach too, and that approach is known as the dimensional analysis approach to derive this formula. What we understand is that velocity v depends on the tension and depends on the mass per unit length, but we don't know the powers of the same. So what we are supposed to do is, this is v directly proportional to the t to the power a and mu to the power p, and then using the dimensional approach we just derive this formula. Let's have a look. This v could be given, it's an L1 t minus 1, and this is equals to, let's say this is tension force, so it's a kg meter per second square, it's an m1 L1 t minus 2 to the power a, and this is mu, which is equals to ml, it's an m1 L minus 1 to the power b. So this is equals to ma La t minus 2a into bracket mb L to the power minus of b. this is equals to L1 into t to the power minus 1. So from this this could be given as a is equals to 0, or I should say, one moment. So if we solve this, this is equals to L1 t minus 1. This is equals to m to the power a plus b, L to the power a minus b, and t to the power minus of 2a. So from this it's minus of 2a is equals to minus of 1. So this is equals to a is equals to 1 by 2, and this is a plus b is equals to 1. So b is equals to minus of half. So this is basically t to the power a mu to the power b, and that's why it's a v is equals to root of t by mu. So this is the second approach, and NCRT has derived this formula based on this approach. So you can use this approach. There is no harm in it. I hope this is clear. So I hope you understand this, that how this could be done. I hope this is clear. Does it? Does it? So please note it down. Please note down this formula, and we are going to use it in our applications. That velocity in a stretch string could be given as v is equals to root of t divided by mu. Is it clear? Is it? Are you sure? Do you have any doubts? Is there anything? Is there? No? Great. So shall we move to the next question? Shall we? Shall we? Great. Let's have the first question of today's class. Let's suppose this is one of the rope, and it is having mass m and unit length L, and suppose one moment, I have given pulse over here, and this pulse has started moving, and let's say this is the point P, and this is the distance x. Yes, so the question is find out velocity at point P. So you want a velocity at point P, you want velocity of wave at point P, that as this pulse has started traveling from bottom of the point to this point. How will you do this? So what I understand is that according to the formula, this is v is equals to root of t by mu. So my first task would be to calculate the t, and another it's a mu. A mu would be very easy because it's a mu is equals to m by L. Now let's work for the tension force. So what we were supposed to find out tension is that the total mass m, total length L, multiplied by that amount of length that I have used, and that is equals to x into g. Yes, this is what we have done in the units. It's a laws of motion. So this is the tension at this point P. Now let's put up the value and get the data done. It's v is equals to root of t by mu. This is simply m by L multiplied by x into g, divide by mu, it's an m by L. So this has gone, and this gone. So this velocity of a wave at point P is root of x into g. I hope this is clear. This is the velocity of wave at particular point P. I hope this is clear. Is it clear? Is it? Do you have any doubts up till now? Is there anything? Is there? No? Great. Now if I extend this question, that this was the point P, yes, and pulse has been started from here. If they ask us that find out time required by a wave from bottom of from bottom of st string to the end of the string. Yes, so you want to find out time required by a string that has started from here and it needs to reach at here. It's the top of the string. So how will we do this? What we understand is that we are having the velocity of this wave, which is equals to v, that is equals to root of x into g. As you can see this, that v is equals to root of x into g. That means it's a variable velocity. It is keep on changing with distance, and if it is keep on changing with distance, what I need to do is I cannot simply write the speed is equals to distance by time. Yes, this is not going to work for me because the speed is variable. So please don't use this v is equals to x by t. Rather, I need to use a differentiation form. It's a dx by dt, that is equals to root of x multiplied by root of g, and from this it's a dx by root of x. This is simply root of g into dt. If I integrate this on both the sides, then this is equals to, this is integration of dx by under root of x, so this is integration of x to the power minus of half into dx. This is equals to root of g integration of dt. So this is from L initial to L final. This is from 0 second to the t seconds. So as it is integration of x to the power minus of half dx, this will be equals to x to the power minus of half plus 1 divided by minus of half plus 1. This is equals to root of g into t. This is from 0 to t. So this is minus half plus 1. This is plus half. Divide by minus half plus 1. This is equals to half. This is root of g into t. And this is 2b from Li to Lf. So from this it's 2 under root of x from Li to Lf. This is equals to root of g into t. So this is 2 under root of L final minus root of L initial. This is equals to root of g into t, or I should say it's a t, which is equals to 2 under root of Lf minus Li divide by root of g. If I took L initial is a 0 because it has started its motion from a very beginning point, and Lf is equals to L, then this could be t should be equals to 2 root of L by g. This would be the final answer. I hope this is clear. Is it? So do you have any doubts? Is there anything? Is there? Do you have any doubts? Do you? Are you sure? Are you sure? Great. Do you have any doubts now? Great. So let's move on and let's do the other question. Let's suppose this is the situation that this is a rope, and with this rope a block has been attached. This rope is having, let's say, mass m and length is L, and this block is having mass m. The question says that if we give a pulse at the bottom end of rope, find out ratio of velocities sorry at point 1 and point 2. This is a point 1, this is a point 2. Try doing this. You are having a 30 seconds for this. Do it quickly. Yes. Can you do this? Yes? Let me help you. What do we understood is this velocity is the root of t by mu, and when this velocity v is equals to root of t by mu, so I need to arrange the two values. One of them is the root of t and another is the mu. So mu is fixed because only one string is there, and it is equals to, sorry, this mu is equals to small m divided by L. So mu is fixed. Now what I need to do is I need to arrange the tension at this 2 points. So tension at 1, as you know that this is the point where only capital mass M would be there for the tension, and this is equals to mg. And if I find out the tension at here, it's a T2 location, then both the mass would be included, and this is equals to capital M plus small m into g. A mu is same for both the cases, and if mu is same, then this could be given as this is equals to v1 is to v2, that is equals to root of t1 is to t2. And when it is such like this, it's an mg divided by m plus m into g, and this has gone. So this is equals to v1 is to v2, this is equals to m divided by capital M plus small m, this is equals to v1 is to v2. I hope this is clear. Is it clear? This is equals to v1 is to v2, which is equals to root of m divided by capital M plus small m. Did this? I hope this is clear. Is it? Okay. Now I want to extend this question at, look at this. In the previous question, find out ratio of wavelength at points 1 and 2. So we need to find out a ratio of the wavelengths at point 1 and 2. How shall we do this? What could be done? So what I'm supposed to do is that this is the situation. This was the situation. This is mass m, length L, and this was mass m. So, and this is the location 1, this is the location 2, and we need to find out the ratio of the wavelengths. So as you understand that at this boundary a wave is being traveled from this, it's from box or from this block to the rope, and in this boundary a wave is going to travel from this rope to the ceiling or to the rigid support. So it is the case of the refraction. Yes. So what we understood is, and you have already studied this in class 10, although it was for the light wave, but that is true for every wave, that when any wave travels from one medium to another medium, it will be having refraction. So when any wave travels from one medium to another medium, it will be having a refraction. And when refraction occurs, when refraction occurs, frequency is the only quantity, frequency is the only quantity that is same in both the medium. I hope this is clear. So when refraction occurs, frequency is the only quantity that is same in both the medium. I hope this is clear. So if it is the frequency that remains the same, what I'm supposed to do is that v1 is to v2, which is equals to f by lambda 1 and f by lambda 2, as frequency never changes during a case of refraction. This has gone. So this is v1 by v2, which is equals to lambda 1 by lambda 2, and we have already calculated the v1 is to v2, which is equals to root of m divided by m plus m. I hope this is clear. So please do understand this. This is a very logical question with involvement of multiple concepts. Yes, it includes the concept of velocity in string wave, it includes the concept of tension force, it includes the concept of refraction. So this is how multiple concept questions can be formed, and this should be done. I hope this is clear. Yes, great. Now let's look at the next questions. Suppose we have given certain arrangement, and that arrangement seems something like this, that this is one of the pulley, and we are having one of the block over here, we are having a second pulley over here. Let me redraw this. Yes, let's understood that this is the one of the block, and let's call this as an M, and this is another block, and we have different strings, that let's call this as a B string, and let's call this string as a C D string. I have been asked that all the strings shown in the figure, all the strings shown in figure are made up of same material, are made up of same material, and having same cross sectional area. The pulleys are light. find ratio of wave velocities in string AB to CD. How will we do this? Go through the data once and let me know what could be done. As we understood that velocity is directly proportional to the tension force. Yes. So if I mark a tension T over here, then in this string it would be the tension T. In this string it would be a tension T. Yes. So if this is the tension T, this will be having a tension of 2T. I hope this is clear. Yes, tension would be if I represent both the tensions. Then what I can do is that velocity, which is equals to root of T, it's a velocity in AB, and velocity in CD, it's a root of 2T. So if I took a ratio of AB is to CD, so it's a VAB to the VCD. This is equals to root of T by root of 2T. This is equals to root of 1 by 2, and this has gone. So this is VAB is to VCD. I hope this is clear. Do you have any doubts? Do you have any doubts? Is there anything? Is there? Are you sure? Great. Now let's discuss a different variation with this velocity. We are having this V is equals to root of T by mu. And when I am having the V which is equals to root of T by mu, I can replace this as this is T. Mu is the mass per unit length, it's a M by L. So this could be varied as T into L divided by mass. Mass is the density into volume. Volume is equals to area into length. So this length L and this length L has been gone, and this is equals to tension by area, which is equals to stress divided by density. So this is could be written as V is equals to root of stress divided by density. I hope this is clear. Is it clear? Yes. One more form of this. We know that it's a Young's modulus which is equals to strain. It's a Young's modulus which is equals to stress divided by strain. Yes. So from this it's a strain which it's a stress which is equals to Young's modulus into strain. So this velocity could be written, could be, this stress is equals to Young's modulus multiplied by strain divided by density. Yes, even a question can be framed from here. Even one more and very good approach to ask this question is, we have a thermal stress, and that thermal stress was equals to y into alpha into delta theta. Yes, so this could be asked, it's v is equals to y into alpha into delta theta divided by density. Yes, so even this kind of questions could be asked. Even there are so many variations, as you understand, once it's a Young's modulus and strain has been opened up, so many different approaches could be created from this, and questions can be formed for this. I hope this is clear. Is it clear? So let's do one of the questions based on it, and let's move on to the new aspect of this question. They said that a copper wire is held at the two ends. A copper wire is held at the two ends by rigid support at 30 degrees Celsius. The wire is just taut with negligible tension. find the speed of transverse wave. Find the speed of transverse wave in this wire at at 10 degrees Celsius. If Young's modulus has been given, and that Young's modulus is 1.3 into 10 to the power 11, units will be Newton per meter square, and alpha of this wire would be is equals to 1.7 into 10 to the power minus of 5 degrees Celsius inverse, and in one density would be required, which is equals to 9 into 10 to the power 3 kg per meter cube. So how will you do this? What could be done? They have asked us about the thermal stress relation. Basically they have asked the velocity, and this velocity v could be, it is equals to root of y alpha delta theta divided by density. So this is equals to root of y alpha delta theta, it's a 1.3 into 10 to the power 11 multiplied by alpha, it's a 1.7 into 10 to the power minus of 5 into delta theta, which is equals to 20, divided by density, which is equals to 9 into 10 to the power 3. So if you will solve this, you will find this, it's a 7070 meter per second. Yes, but you need to solve this. Please do it. I hope this is clear. So this kind of questions could be asked. I hope you are clear with this approach and this concepts. Yes. So our first part, as we have discussed here, that we are going to deal with this two parts. This that has been the wave that has been produced in the stretch string is done, that we have discussed that, and now we are going to discuss about the velocity of the sound waves in different mediums. So let's have a look how we will deal with it. So now it's a speed of longitudinal waves, or basically it's a speed of the sound waves. So in a longitudinal wave, the constituents of the medium oscillates forward and backward in the direction of the propagation of the wave, and we have seen that in the lecture 01, that sound wave travels in the form of the compression and the rarefactions. So when it travels from the compression and rarefactions, the elastic property that determines the stress under the compressional strain is the bulk modulus of the medium. So basically whatever we are having at that time, it's a stress by density. This stress can be, now the stress can be replaced by the bulk modulus B, and density remains as it is. One more approach is that let me check the dimensions of B divided by rho, and that is equals to V square. So what I can have is, this is simply the V, which is equals to root of B divided by rho. Yes, so the speed of a longitudinal wave through a fluid depends only on its bulk modulus P and density rho. I hope this is clear. Is it? Great. So if B and rho are considered to be the only relevant physical quantities, a general formula for the velocity of a longitudinal waves in a liquid, it's a V, which is equals to root of B by density. Yes, and a same way speed of the longitudinal waves in a solid bar, that could be given as V is equals to root of Y divided by density. I hope this is clear. Is it clear? Is it? Are you sure? Yes, as we understand that a speed of a sound wave speed of sound wave is maximum when it travels through solids, and and it is minimum when it travels through gases. So basically this is speed of a sound wave in solids is greater than speed of a sound wave in the liquid is greater than the speed of the sound wave in gases. So it's solids, liquids and gases. This would be the correct approach. I hope this is clear. Yes, does it clear? Do you have any doubts? Is there anything? No? Great. So let's look at certain quick questions. The question says that the speed of the transverse wave in a straight string, yes, it's a v which is equals to root of t divided by mu. A second, the speed of the wave, yes, it's a v which is equals to lambda by t, and this is equals to lambda into 1 by t. While I use a 1 by t, it's a frequency, and this is equals to f lambda. It's n into lambda. Yes, great. Next, the general formula. The general formula of the speed of the longitudinal wave in a solid bar. The speed of the longitudinal wave in solid bar, which is equals to v is equals to under root of Young's modulus divided by density. When I use it's a root of b by rho, this is in liquids, this could be in liquids. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? No? Now let's discuss estimation of the speed of the sound in the gases. How speed will be having, or how the speed is traveling in the gases. Let's have a look. So for speed of the sound in gases, initially Newton have worked over it, and first we will discuss what Newton's formula for speed of sound is. So what Newton has considered, that he has considered that the propagation of sound in air is the isothermal process, and if he has taken it, or if he has considered it as an isothermal process, then according to the isothermal process this temperature is the constant. And if temperature is constant, this is P into V, which is equals to constant. If P into V is equals to constant, then this is equals to P delta V plus V delta P is equals to 0. From this, it's a P which is equals to minus of V into delta P divided by delta V, and it is equals to P which is equals to minus of delta P divided by delta V by V. A negative sign is here because as the pressure increases, the volume will decrease. Yes. Now as we understood that bulk modulus B, which is equals to pressure of gas, if you have remember the unit which is mechanical properties of solids, we have isothermal elasticity of gas. Yes, and that was the B is equals to P. We have one more elasticity which we are going to use in near future. It is the adiabatic elasticity. And this adiabatic elasticity was B is equals to gamma times of P. So this was the adiabatic elasticity. Please do remember this. So from this speed of the longitudinal wave in an ideal gas, is V is equals to root of P by rho, and this has been derived according to the Newton, that a sound wave travels with the help of a sound wave travels or according to the isothermal process, and they have derived this. This is equals to Newton's formula, which we can given as V is equals to root of P by rho. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? Do you? Do you have anything? Any doubts? No? Great. But the problem arises that when we try this, if I put up a value of pressure, if I put up a value of density, then whatever the velocity of the sound wave that we received in air is approximately, this is the theoretical value, is 260 meter per second, while the practical value is approximately 320 or 330 meter per second around. So whatever the Newton has assumed and that we put up the data, then it is approximately 250, 260 or maybe 270 meter per second. And whatever the number that practical observation says that it is or it should be a 320 to 330 meter per second. Yes. So when this happens, we understood that there is certain error in it, and if there is certain error in it, there must be certain correction is required in this formula. So basically then Laplace has given the correction, and what correction he has given, let's discuss. So according to the Newton, when sound propagates through air medium, temperature of the medium remains the same, and he has considered that this should be an isothermal process. But according to the Laplace, when sound propagates through air, a medium of the temperature changes, and this should be considered as an adiabatic process. Even one more variation was there. Newton has considered that this compression and rarefaction was taken place at a very slow rate. That is what we call as a quasi-static process. Yes, but Laplace said that this could not be the slow process. This is very rapid process. That compression rarefaction must be occurred at a very high rate, at a very rapid process, and this is how sound propagates. So from this it's a p into v to the power gamma, which should be equals to constant, and according to the adiabatic, yes, according to the adiabatic, which is equals to pv to the power gamma, which is equals to constant. And if I differentiate this, this is equals to p into gamma into bracket v to the power gamma minus 1 into delta v plus v to the power gamma into delta p, this is equals to 0. So if I'm replacing this, this is equals to gamma into p, which is equals to minus of delta p divided by delta v by v. And as we have derived, it's a b of an adiabatic, which is equals to gamma into p. So this is b into adiabatic, which is equals to gamma into b of isothermal. So according to the Laplace correction, speed of the longitudinal wave in an ideal gases should be equals to v, which is equals to under root of b of adiabatic divided by rho, and b of adiabatic, it's gamma times of p divided by rho. So if I put up this value, gamma as a 1.4, 7 by 5, it's a diatomic gas. Yes, what we are achieving is approximately, this is 330 meter per second. Yes, and which matches almost with the practical aspect. So we understood that yes, it was Newton's mistake to consider compression and rarefaction as an isothermal. It could not be an isothermal, but it should be an adiabatic one. So this is the correction by Laplace in the speed of the sound wave in gases. So this is the correct formula. V is equals to under root of gamma p by rho. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts? Do you have any doubts? Is there any? No? Great. Now from this it's a gamma into P by rho. We are having this relation which is equals to P into V, which is equals to nRT. It is something like this: P into V is equals to nRT, and this N could be given as M by M into RT. If I divide this volume to the mass M, it's a M divided by volume, it's a mass by volume, which should be a density. So this is equals to gamma into RT, it's a density into RT by M. And this P by density, it's a pressure by density, could be given. This is equals to V is equals to gamma RT by M. I hope this is clear. So please keep this noted. We are going to use this sooner, and we are going to use questions based on this. So please note this. Also, please keep in mind that if exams has asked me that what is the velocity of sound wave according to the Newton, then please write the formula which Newton has given. Now as we know that it is the incorrect one and everything is okay, but if they have specifically mentioned it, that give the formula for the sound wave as given by the Newton, we need to provide whatever has been asked. Yes, I hope this is clear. Yes, great. So this is V, which is equals to root of P by rho. This V is equals to root of P by rho, that this was given by the Newton, and we are going to provide this only. I hope this is clear. Is it clear? Great. So as we have discussed, velocity in solids is greater than velocity in liquids, and which would be greater than in the velocity of the gases. I hope this is clear. Is it clear? Great. Let's look at certain quick questions. The velocity of sound is maximum. Yes, velocity of sound is maximum in solids. The velocity of sound, which is minimum in the gases. The Laplace formula is V is equals to under root of gamma P by rho. Yes, so this was the relation given by the Laplace, and for all our numerical needs we are going to use this. Let's have a certain variations on based on this. It's a gamma into P by rho, and when this is equals to gamma into P by rho, we understand that we have already derived this. It's a V is equals to gamma into RT by M. So if I understood this very well, then what I understand is that first, its velocity is independent of pressure if temperature is kept constant. So if temperature remains the constant, velocity is independent of the pressure. Second is velocity is 1 by root of density, or velocity is 1 by root of molecular mass if again this temperature is constant. And when I say its a velocity is under root of m, I mean is that velocity of sound wave in hydrogen gas is maximum. Yes, velocity of sound wave in hydrogen is maximum because it is having the smaller the mass, maximum would be the velocity. Next variation could be that velocity of a wave depends Velocity of a wave depends on medium, but not on the frequency of source. Yes. Next very important aspect is velocity is directly proportional to the root of T, while T is the absolute temperature. T is the absolute temperature. Please, it's a request, always use in Kelvin. This could not be considered in degree Celsius. So please keep this in mind. Velocity is directly proportional to the root of T. And last but not the least, that velocity of sound wave, velocity of sound wave in dry air is greater than moist air in certain cases. I hope this is clear. Is it clear? Is it? So these are the variations. These are the variations that affects the speed of the sound wave in the gases. So are you ready for the question? Are you? Let's have a look. If pressure of a region is 4 times the initial value, find out change in velocity of sound wave in gases if temperature remains constant. So if temperature remains constant, we need to find out the change in velocity if we have changed the pressure. How shall we do this? How shall we do this? So we have the relation which is equals to V is equals to gamma P by rho. So if P dash is equals to 4 times of P, and as it is in square root, this is V dash which is equals to 2 into V. Yes. How many of you think like this? How many of you? There are many. Yes, I'm sure for this. But this is absolutely incorrect approach. You cannot think like this. They have given temperature remains the constant. So what is situation that even we have mentioned it over here at a very first point, that velocity is independent of the pressure if temperature is kept constant. Why so? Let's have a look. We have the relation which is equals to PV is equals to nRT, and from this it's a P is equals to M by V into RT by M naught. So this is equals to P by density is equals to RT by M naught. As they have mentioned that R is always constant, M naught is always constant, even T is constant, because they mentioned that temperature remains the constant. So this P by density is constant. So it means if P dash is equals to 4 times of P, then even density or new density will be 4 times of initial density. And if such is the case, then V dash would be equals to under root of gamma into 4P divided by 4 density. This has gone, and this is equals to V itself. I hope this is clear and you understand this fact. Do you? Do you understand this fact? Are you sure? So do you have any doubts? Is there anything? No? Great. So let's wind up this session over here. This was all about the velocities of the wave. We have discussed two different categories of the waves. One is the velocity of a wave when they were traveling in the stretched string, and another is the velocity of the wave in the solids or liquids or gases. Basically, they were the sound waves. So please revise this. Please check all the facts. Please check all the formulas, because this are having a small logical questions that is based on the concepts. So please go through this and practice this a lot. Practice can save us. Thank you. Have a good day. Take care. Bye bye.